Charles Babbage was an English polymath, mathematician, philosopher, inventor, and mechanical engineer, who was born in 1791. In that time, printed mathematical tables, for example for navigation, were still calculated by human computers. In other words, by hand. Repeating mistakes were known to occur in transcription as well as calculation. And it also was just a lot of exhausting manual work. Babbage once said, "I wish to God these calculations had been executed by steam." To solve the problem, he first designed a difference engine that was able to compute values for polynomial functions. But he never finished the complete machine, probably also because in the meanwhile his attention had moved on developing a far more sophisticated thing, namely the analytical engine. It was in 1833 and he was 42 when he started this work. And interestingly, in the same year he met Augusta Ada Byron King, Countess of Lovelace. Or a little bit simpler, just Ada Lovelace. She was 17 years old, already a mathematician, and very interested in Babbage's ideas. Charles Babbage, on the other side, praised her analytical skills and later called her lovingly Lady Fairy. In the following years, with some interruptions, Babbage worked on the design of the analytical engine and developed in total 28 different plans for it. Ada saw the potential of his invention and wrote several programs for the theoretical machine. That's why many people see her as the very first programmer. Babbage created this trial model for the analytical engine and documented his ideas in about 1,000 notations and 7,000 manuscripts. His son Henry also finished another part of the machine in 1910. But in the end, the complete machine was never built. Despite all this, the concepts were really brilliant, and Charles Babbage was probably 100 years ahead of his time. So let's have a closer look on how this machine should have worked. The comic writer Sidney Padua imagines the analytical engine as follows. Isn't it beautiful? In front of the machine, Mr. Babbage smiles and seems quite confident. On the right-hand side, Lady Ada Lovelace, a little bit dreamy, reads a long row of punch cards. The machine is really huge and therefore a strong steam engine is required to drive it. The first part of the program is located on the operation cards, which are processed by a reader device and define which arithmetic instructions should be done by the machine one after another. The instructions on the cards are encoded in holes, which are decoded then by the reader and afterwards passed to the barrels that define a sequence of smaller operations which then are executed by the mill. The barrels together with the mill implement the four basic arithmetic operations, namely addition, subtraction, multiplication and division. The program data is located in the store, where in total 1,000 decimal numbers with 50 digits each can be saved. Each number is implemented by a stack of 50 gears and has a unique column number, which is used for addressing. The numbers are loaded into the mill by transfer commands that are encoded on the variable cards. This is the second part of the program and contains the load store instructions to transfer numbers using racks between the store and the mill. The somehow odd separation of variable and operation cards probably had technical reasons. The input data is loaded into the store with number cards, and the results can be put on paper using a printer device. So that's it. Sounds somehow familiar, doesn't it? And indeed, Mr. Babbage has designed, already in the 1840s, an almost modern computer. We just would name the components a bit different in our days. The mill is called today the CPU, or processing unit. The barrels store the microprogram that contains smaller steps for implementing the arithmetic operations. Then of course the store is today called the read-write memory. The operation cards, together with the variable cards, define the read-only program, which is located on the punch cards. One can argue that also the number cards are part 3 of the program, namely the constants, but they can also be seen as input data, similar to data entered by today's keyboards, where a user types in the numbers for the program. Then of course the printer is today called still the printer, but since it is the main output device for the analytical engine, it had to also fulfill the functions of today's monitors, for example. And last but not least, the steam engine. Well, of course, this is a bit old school, and modern machines use electricity instead of steam. So, in principle, everything is there what modern computers have. Since the program is separated from the memory, the analytical machine is not a von Neumann computer, but instead it follows the Harvard architecture. By the way, one of the first computers with that design, the Mark I, was built in the 1940s, almost exactly 100 years after the analytical engine was invented by Charles Babbage. So now let's open the engine and look a little bit more into the details. We see again the store with 1000 stacks of gears, one for each number. With the number cards we can feed data into the store. The mill consists of a very complicated set of mechanical parts for doing the micro instructions orchestrated by the barrels. As input for the arithmetic operations, a so-called ingress axis is used, which can store a 50-digit decimal number. At least logically, there are even 2 ingress axes. So for simplicity, we added a second one. The 2 ingress axes are basically what we today would call input registers, and they are used as operands for the arithmetic instructions. The result of a calculation is stored in the egress axis, which also can hold numbers with 50 digits. There are racks that connect the ingress and egress axis with the store. Today we would say that is the memory bus. The variable cards instruct the racks to copy column contents from the store into the ingress axis and copy back the result data from the egress axis. The operation cards define which arithmetic functions should be done. And besides that, they also can instruct a bell to ring, or they can halt the whole machine. Now that we know all the important pieces of the analytical engine, it is time to run a program on it. Fortunately, Ada was so kind to develop a good example and created the required punch cards for us. For some strange reason, Mr. Babbage wants to prevent her from running the code. The question is why, since the program is really simple. Ada just wants to calculate, as an example, 24 plus 18. Before we start, we should mention that the 3 streams for number, value and operation cards somehow have to be synchronized. It seems a bit unclear if Babbage ever explicitly defined how that should work. So for simplicity again, let's assume that the selection of the correct card stack is done by magic. So let's start the program. In the first column you see the step number. In the second there are assembler-like instructions, and in the last column there is a short description of what is going on. First two number cards are read to load number 24 into column 5 and then number 18 to column 6. Then the first operation card is read, which is an addition. This configures the barrels for adding two numbers, which are read in the following steps. Next we read two variable cards, which first load the number 24 from store column 5 into the ingress axis 1, and then the number 18 from column 6 into ingress axis 2. To achieve that, the data is transferred by the racks. Now the ingress axes are read by the mill, which is then doing the addition under the control of the barrels. The gears are performing their magical work when they are doing the arithmetic operation. After the calculation is finished, the result is written to the egress axis, which we would call today an output register. Then the next number card is read, which instructs the racks to save the contents of the egress axis back to column 7. Finally, we print the last result, ring the bell, and halt the program. So the answer is 42, which is obviously right, and by coincidence exactly the age of Mr. Babbage when he first met his lady Fairy. So that was a brief summary of what can be found on the internet for the analytical engine. But there are still some more details worth mentioning. The machine has a run-up lever that indicates exceptions like overflows or sign changes. The indication can then be used for conditional branches that are able to wind the punch cards forwards and backwards. And this feature, together with the store, makes the analytical engine probably even Turing complete. The machine somehow also implements pipelining, meaning parallel computation. Nevertheless, the speed of the machine seems moderate. People are guessing 3 seconds for an addition and 3 minutes for a multiplication. Last but not least, there is an emulator available on the internet, where we can try Ada's program. Indeed, having an emulator is really cool. But the proof that this machine could also have worked in reality is still missing. Therefore, in 2010, a project called Plan 28 was initiated by John Graham Cumming, who in a TED talk described Babbage's ideas. The machine should be built and finished in the 2030s, 200 years after it was originally designed. Plan 28, from which the project takes its name, is the most complete of Babbage's designs. Doron Zwait, former curator of the Science Museum, London, and involved in the 17 years reconstruction of the Difference Engine No. 2, in 2012 estimated that the project would require 15 to 20 years and $20 to $40 million. The machine would be 10 times bigger than the Difference Engine, would weigh several tons, and it would probably need 50 to 80,000 parts to build it. So it looks like a really challenging plan. Good luck for our British colleagues. Would be so great to see the machine up and running.